Hello, Stats class. This is lesson 12.1b, which, as you probably could have guessed, is about confidence intervals for slope. So we're going to do a little bit more with the sampling distribution first. I want to remind you that b is our estimated slope, which we get from the sample. And we're going to use it to predict the true slope, which is called beta. And that is the slope we would get if we could use the whole population to calculate the slope. So before we can do the confidence interval part, I want to talk about the sampling distribution of B. We talked about it a little bit in 12.1a, but let's expand that a little bit. So remember that B comes from a sample, and each time we take a sample from our population, we get a slightly different B value. And so this varies depending on the sample. So before I list the shape, center, and spread, I'm just going to draw a quick picture to remind you that we have our beta, which is the true slope. And then sometimes B will come out a little higher than beta, sometimes B will come out a little lower than beta. Bunch of dots representing all the different possible slopes I could get from different samples. So each of these represents a separate B value from a separate sample. And what we would hope would happen is that these would be clustered, centered around the beta value, the true value, and they would be a predictable normal curve. Would be really nice, wouldn't it? Turns out that they do form a normal curve, and we're not going to prove that or anything like that, but the shape of the sampling distribution, yes, you guessed it, is approximately normal. It makes me so happy that we can use what we have learned before about that. Smiley face, because we're happy that that works. The shape is approximately normal if the conditions are met. Remember we talked about conditions and there were 5 of them? And those there were 3 conditions that have to be, you have to look at the graph to get those conditions. So if those particular 3 conditions are met, that would be the normal condition, well, that's logical, and linear condition, and equal variance condition. These are the ones you have to look at the graph for, and all of those, if they are true, then the shape of the sampling distribution of the B's is approximately normal. So these are the ones that we look at a graph to check, and that's all about the shape. Good news is it's pretty simple. It's like if those are met, it's approximately normal. We don't have to worry about it other than that. Center. Well, what we would hope is that it's an unbiased estimator, and it turns out that it is, that these different sample slopes are sometimes above, sometimes below, but centered at beta. So that would mean the mean of all the B's is beta, and that means that it is an unbiased estimator, which is why we're studying it in this class. We're not going to do the biased ones. That'll be a later stats class that you might take in college. So an unbiased estimator is true if you have a random sample. That's the condition that causes that to be true, and that's the reason we check that condition, either randomly assigned treatments or a random sample. So that's also pretty simple. Spread is last because it's a little bit more complicated, and so that's what the warm-up was about. The warm-up was about things that affect the spread of the slope, the variation in the slope. Variation in the slope is affected by 3 things, and the things that was affected by 2 of them we did in the warm-up. So I'm going to remind you that we talked in the warm-up about the variation in X making a difference, and the variation in Y. And we talked in the warm-up also about the variation in X, large is good. We want the X's to be far apart. And variation in Y, small is good. And I hope you watched my little video about the meter stick demonstration where I showed you why that makes sense, that the variation in X, we want it to be large, and the variation in Y, we want it to be small. And then also, we didn't talk about this in the warm-up, but it's affected by sample size. And you've seen that before. Bigger samples give you better estimates or smaller spread. So in general, sample size, large is good. And when I say good, I'm specifically talking about reducing the variation in slope. We want the variation in slope to be small so that our estimates are close to the actual value. So all of that gets put together into this formula for the spread, or the standard deviation of the slopes. That's the standard deviation of this sampling distribution. And here's the official formula. It is sigma over sigma x square root of n minus 1. So let's talk about the pieces of this. The sigma is the population version of S, which is the standard deviation of the residuals. And the standard deviation of residuals, remember, is the vertical distance off the line, which is basically a measure of the variation in Y. And the reason it's on top is that if Y varies more, then the slope varies more. And if Y varies less, then the slope varies less. So that's a direct relationship. The sigma x on the bottom is the standard deviation of the x's. And that's the representation of variation in X. The reason it's on the bottom is because larger variation here, when you divide by a larger number, you get a smaller variation over there. And then same with the N. N is on the bottom because of the same thing. Larger N's mean smaller variations in general. So this is the effect of the sample size. So now this formula only works if you know the population values. Notice all these Greek letter sigmas mean that we have to know the population standard deviation of the residuals. We usually don't know that, and so we usually estimate this value based on the sample, just like we've always done. And the estimate, when you estimate a standard deviation, it's called a standard error, so that's called SEB. Some people call it SEB. I've had students in the past who find that fun to call it SEB. But anyway, you just replace the sigmas with S's. And the S is the standard deviation of the residuals that we have seen before. The SX is the standard deviation of the X's from the sample, and then n minus 1 square root is just there. But I wanted to remind you again that this is the variation in Y over the variation in X, and a little bit about sample size. And it should remind you of Y over X being used for rise over run. This is, we're talking about slope here, so that shouldn't be a problem. Now, I have really good news for you before we go on, and that is most of the time you will not have to use either one of these formulas. The only reason they're here is I wanted you to understand some of the influences on the spread, because it's, interesting, but usually we don't have to calculate this. Good news. The calculator or computer will do this part for us. So I have never seen an actual AP problem where they make you use this formula. There might be something in your homework about that, but there will not be anything on the quiz where you have to use this formula. It's just there because I think it's interesting. So hey, I hope you thought it was interesting too. What I'm going to talk about next is how to calculate the confidence interval for the slope and what you actually do have to do instead of using that formula. So this part was all of the sampling distribution, and now we're going to switch gears a little bit and talk about calculating the calculation step of the confidence interval. We've already talked about state and plan. State is the same as you've always done, and I'll do an example if you need it, but calculating confidence intervals for slope. We're going to talk about the do stage. So, all confidence intervals have the same pattern. They are always a statistic or estimate plus or minus a margin of error And that statistic, you could break down the margin of error into two pieces, of course, which is the critical value times the standard error. And the standard error, theoretically, you could find it by using this formula if you had the data, but you don't have to, because you are going to usually be given the standard error as part of your computer output or whatever they give you. So the statistic in this case is B for the sample slope. Critical value, you'll be really happy to hear, is a familiar one. We don't have to learn a new type of critical value. It is T star. Done T star before, and then we multiply by the standard error, which is SEB, or SEB. And the T star is going to be found the same way we found it before. If you have a TI-84, you're doing inverse T. The area is the confidence level plus half the extra. We've seen that before. Then you'll put DF. If you don't have a TI-84, you'll be using probably the GeoGebra probability calculator and doing almost the same thing. DF in this chapter, here's something new, is n-2. Oh my goodness, it used to be n-1, and then we changed it to categories -1, and now it's changing again. What's with that? N-2, the short answer is because there's two variables now. Two quantitative variables means we have a n-2 as our DF. So now most of the time, you can do this on your calculator, and the calculator will, the newer calculators have a shortcut and all of that. The most common thing on the AP test and in your homework is to use computer output. And so often they will give you computer output and say, use this to do your confidence interval. And I want to just talk about that because we've seen the computer output before. When we did chapter 3 and we did finding the line of fit on there, and I told you there was some other stuff on there that we didn't need. Now we're going to learn how to do some of that other stuff. So we always have a predictor and a coefficient, an SE coefficient. That's the standard error that I was just talking about, and a T and a P. And I'm going to give you the computer output from the rows and scores that we did in the warm-up for 12.1a. So I'm going to use warm-up 12.1a example. If you didn't do that warm-up yet, you probably should go back and look at it. So this is always constant. This is row. I'm going to just write it out, and then I'm going to talk about each piece and where you would find the stuff you need on here. Some of it you already know where to find it. So I'm just copying it off of my computer output that I have on the side. Some of these numbers should look familiar to you because if you did that warm-up, you saw the slope and the y-intercept already. So they should look familiar, I hope. Alright, I'm going to put a box around this because usually it's in a box when you see it on a quiz or in your homework or on the AP test. So there is the official computer output. I'm going to grab a different colored pen and I'm going to talk about where to find what you need. So some of the stuff on here we already know. We already know that these two numbers are the slope and the y-intercept. Officially they are called A and B. A is the y-intercept and B is the slope. Technically, those are the sample y-intercept and the sample slope. They are estimates of the actual. So I'm going to put a little arrow down here and say A is the estimated y-intercept. B is the estimated slope. Remember, the parameter that comes from the population would be alpha and beta. So technically, this is our estimate of alpha, and this is our estimate of beta. Okay? We've talked about this in chapter 3, that this right here is the name of your x variable. And when you're writing your equation, you use that by saying this is the constant or the y-intercept, and this is the number that would be the coefficient of x. And so in chapter 3, we learned how to just use this piece only and write an equation. Chapter 3, we learned how to write an equation for this, where we go y hat equals 85.95 minus 1.517x. This is the same equation we found in Desmos when we were finding the equation of the slope. And remember that y hat is the predicted score on the final exam, and x is the row number of the randomly assigned seats of these students. So in case you forgot the context, that's what it is. So we learned that back in Chapter 3. Yay, we already know that part. We also in Chapter 3 learned how to interpret this piece right here, which is the standard deviation of the residuals. Or it's how much the predictions are off by. It is calculated from the sample, which is why it's an S. The sigma, or this sigma that's up here, the Greek letter that goes with it would be the standard deviation of the residuals if we had the whole population. So this is an estimate of the true standard deviation of residuals, which is called sigma. We also learned how to interpret this in Chapter 3, which is R squared, which is the correlation squared. And we learned that that is the percent of the variation in y that's explained by x. And we did all of that. I'm just going to put ... because I hope you remember that, but it's not important for today. So that's the stuff we already knew, right? That's kind of a lot of stuff that we already knew. But back in Chapter 3, I told you to ignore all this stuff because you didn't need it, right? Well, now we need it. SE. SE, that sounds like a standard error. I want the standard error of B. That would be right next to B on this table. This right here is SEB. If you really want to know, the one above it is SEA, standard error of A, but we're not going to worry about y-intercepts. We're not going to try and predict them or do confidence intervals for y-intercepts, although we could. We need this one that's right next to the slope. And then these ones we're going to use tomorrow, or not tomorrow, we're going to use those on Monday. These are for significance tests, which we will learn about on Monday. And so the main new thing that you need is this right here. That's SEB. That's why you don't need that formula so much, because the computer output gives it to you. So in Chapter 12, we not only can write an equation, but we can do a confidence interval for the slope using this information. So let's do that. Confidence interval, let's do 95% because it's the most normal one, most usual. So we're going to start with our B plus or minus T star times SEB. That's my formula. B, I read off of the table. It is negative 1.517 plus or minus. I need to find T star, so let's do that over to the side. It is inverse T. 95%, 0.95 plus half the extra is 0.975. And then DF, remember we had 30 students in this class, and so I would do 30 minus 2, which is 28. And I would get out my calculator and do stat second vars and inverse T. And of course you would do it online if you don't have this graphing calculator. 0.975 and 28, because I did it before I started these notes. There it is. It is, drum roll, 2.048. That is T star. I should put that over here too. And then SEB, I just get off the table, 1.332. It's like the easiest calculation of a confidence interval we have done this year, because most of the time they give you this table, and look, 2 of the numbers you need are right there. Put them in your formula. And then I multiply, and I add and subtract. So let's do that. Negative 1.517 minus 2.048 times 1.332. And I got negative 4.245. And then I do it again with a plus sign. 1.211. All right, so before I do the conclusion, I want to point out that if you have a TI-84, there's also a calculator shortcut that is a linreg t-int. It's at the very bottom of the list on stat tests. So if you have a TI-84, It won't work on an 83 because they don't have that, which is too bad. You could do lin-reg-tient on stat tests. And I don't use that very often, actually, because it only works if you have the data in a list. I think I do have the data in a list. Yes, I do. List 1 and list 2 are my data from the rows and columns. And so if I go back to where I just was and do lin-reg-tient, and I tell it to look at list 1 and list 2, and I tell it which confidence level, I don't really need this piece, just leave it blank, calculate. That's going to give me the same answer. Negative 4.245 and 1.21. Oh, they rounded up to 2. Okay, so maybe I probably have a round off error in there somewhere. It's okay. And last but not least, we write a conclusion. We are 95% confident that the true slope for score versus row number, that's the context, is between negative 4.245, 245, and 1.211 or 2. So you could get even better than that by interpreting what this slope means. Remember, we interpreted it in the warm-up, the last lesson warm-up, as saying that this is how much scores drop every time you move a row back, except this is how much they go up, and this is how much they drop. They might drop by up to 4 points, or they might rise as you move further back in the room by as much as 1.2 points. So that's interesting. Drop this much per row, or rise or add to this much. And as you may have noticed, one of these is negative and one of these is positive. That means 0 is in the interval. What does that mean? We've done that before. That means that this is not a significant relationship here. It might be negative, it might be positive, it might actually be 0. No significant relationship between row number and score. And we saw that when we looked at the graph, actually, we kind of predicted that. And then we saw it again when we looked at the randomization simulation in the warm-up 12.1a. You can also see it here in R squared. 4.425% of the change in score is based on row, and the rest of it comes from something else. So most of the variation in scores is not because of rows, it's because of something else. So that is all for these notes. Thank you for listening, and I will see you on Monday.